HNO3. This is the formula for the nitric acid, that is HNO3. Why we are calling it an acid? Because it on dissociation will give us H positive ion and NO3 negative ion. Due to this H positive ion, we are calling it an acid. It possesses the properties of the acids. Then we have the introduction of the chapter. Since the nitric acid was initially called the aqua fortis, you have learned the names of the rest of the compounds also, like the sulfuric acid was known as the oil of vitriol. Then we have the HCl was known as the muriatic acid. Similarly, the nitric acid is known as the aqua fortis. So in the 8th century, alchemists called the nitric acid aqua fortis. The aqua fortis meaning was that it was a strong water as the result of its corrosive action, being dissolved, ability to dissolve in the water. It has its corrosive nature. Thus, then came the Glauber, the scientist. He prepared the nitric acid by distilling niter, that was called the KNO3, with the concentrated sulfuric acid, and hence he named it as a nitric acid instead of aqua fortis. The lastly, Cavendish determined the composition of the nitric acid, the elements from which it was composed of. Talking in terms of the occurrence, where we can find this nitric acid, it occurs in the free state as well as in the combined state. In the free state, it occurs during the lightning discharge. Since nitrogen is present in the atmosphere, so during the lightning discharge, the nitrogen in the atmosphere, it reacts with the oxygen to form the nitric oxide, and thus this nitric oxide gets further oxidized to the nitrogen dioxide. This you may relate this particular paragraph with the acid rain also. So thus the nitrogen dioxide formed dissolved in the atmospheric moisture, and thus in the presence of it forms the nitric acid. So similarly, you can come to the conclusion that nitric acid is not in the free state as in the natural form. We get it from the oxides of nitrogen. From the atmosphere, we have the nitrogen gas. When it reacts with oxygen, that it forms the nitrogen dioxide, nitric oxide, which nitric oxide further oxidation gives us nitrogen dioxide. The nitric acid, it falls on the earth along with the rainwater. That's why we call it as an example of the acid rain. The conversion is shown here with the help of reactions. Firstly, the nitrogen, which is found in the atmosphere, react with the oxygen to form the nitric oxide during the lightning discharge. This nitric oxide further oxidation gives us the nitrogen dioxide. Then we have the nitrogen dioxide with the water vapors present in the atmosphere with oxygen gas gives us the nitric acid, which occurs in the form of acid rain. Thus, the nitric acid reacts with calcium carbonate to gives us calcium nitrate, water, and carbon dioxide. Carbon dioxide is the gas.
I'll be back in just.
Okay.
Yes.
Yes. So further, I was telling you that the nitric oxide in the combined state occurs in the two forms. These two, both the forms are very important. The child saltpeter and the Bengal saltpeter. The name and its formula both are important. So the child saltpeter is named as sodium nitrate, and the Bengal saltpeter is named as potassium nitrate or the niter. Right? It is asked in the paper the name of the formula and its combined state. Then we have the laboratory preparation, the preparation of the nitric acid. The preparation of a nitric acid, talking in terms of the apparatus which we have used, you can see we have the round bottom flask which is kept here. We have the Bunsen burner. We have the clamp stand method. We have a test tube. Then we have the the tilted round bottom flask. And again, an outlet has been given to us. For the reactants, we are taking the sodium, as we have learned the two combined form, the child saltpeter and the Bengal saltpeter. So we are taking here the potassium nitrate and the sulfuric acid. Both are the concentrated form. The potassium nitrate also and the sulfuric acid is also in concentrated form. So as you can see, the both are in the liquid form. So thus both the reactants are in liquid state. When they both are heated at the temperature which is above 200 degrees Celsius, we got we get the potassium bisulfate along with the nitric acid. And as you can see, it has H included in the formula, so it is an example of the acid salt, right? So further you can see when the nitric acid is formed, the fumes are formed here. Are you getting?
Yes, ma'am.
Hmm. Then moving towards our second preparation, we can prepare from the salt of potassium also, and we can prepare from the salt of sodium also. When we are using sodium nitrate along with the concentrated sulfuric acid, we are getting sodium bisulfate and nitric acid. In both the cases, vapors are obtained from the nitric acid since it is fuming, right? And its concentrated form is highly corrosive in nature. That's why, as you can see, a tap has been provided for the continuous cooling of these nitric acid vapors. Then talking in terms of the reactants here, the sodium or the potassium nitrate is distilled with concentrated sulfuric acid. As you can see in the reactants, we have taken sodium or potassium along with the concentrated sulfuric acid. So why we have taken here the concentrated form and not the dilute or other acid? Because the concentrated sulfuric acid is strong non-volatile acid, and non-volatile, I told you that it is capable of displacing the more volatile nitric acid. Thus, concentrated hydrochloric acid was not used because in the place of concentrated sulfuric acid, HCl is very volatile and thus it will displace itself, and it is not used to displace another volatile acid. That's why it is concentrated sulfuric acid is
But
preferred.
if we will use, we had studied in the sulfuric acid chapter that when we take a pure sulfuric acid, it displaces by forming more strong acid. So concentrate, and it is also and it is also a good, what we
And it is
say that
also,
dehydrating agent.
so the work of dehydrating agent is to remove the water content, and we don't have water content in the reactant form. The
No,
water
because
is not mixed with the nitric acid. As you can see, we are just pouring it outside the flask, the round bottom flask.
it is not there in the preparation. It is just to cool.
Yeah, it is acting just as a coolant.
But the glass will break, right? Because the warm air will exert some pressure on the glass, and then the if cold water is poured, the pressure will be unequal, and the glass may break.
That's the drawback of the apparatus. That's why we have maintained a particular temperature here above 200 degrees Celsius. It can go up to high, but we have to keep the apparatus temperature maintained. That's why, as you can see here, it has been written, because since we are using all the glass apparatus, so the glass apparatus which we have taken is a glass retort, and water cooled receiver is done. So this apparatus may tend to crack. This is the drawback. It can be the drawback. That's why the temperature is controlled. The reaction is in the controlled way carrying out. The complete apparatus is made of glass, so the vapors of the nitric acid, being highly corrosive, may attack the rubber or core. That's why we have used coolant to just cool down its temperature, the nature. So as you can see, the two temperature has been given to us above
Ma'am,
or
this
around 200.
concept is there in 11th, the
Yes.
preparation practical of this nitric acid.
No, the preparation of nitric acid is not in your practicals of class 11. It is not in the syllabus also. Not in 11, not in 12th.
Just in 10th.
Just in 10, just to have an introduction.
Because this is more of an industrial process than of the
Yes,
chemistry part of
we
it.
cannot carry out in schools this particular method.
It
It
is
is
done
having very
in,
high amount of risk is there.
yes, 200 degrees Celsius. That's very.
Yeah. So that's why, as we can see, the two temperature has been provided to us above 200 degrees Celsius and around 200 degrees Celsius. So when the temperature is less than 200 degrees Celsius, we are getting sodium bisulfate. So this reaction is preferred, but not temperatures above 200 degrees Celsius. Then the glass retort may crack, that point you are saying. Then we are having sodium sulfate Na2SO4 and HNO3. So from the above two reaction, this method is preferred and not this one, because the first method, the first drawback, that the glass apparatus is entirely made up of glass, it may tends to crack. Similarly, the second one, the further decomposition of the nitric acid. If we are taking here nitric acid, so nitric acid may further gets decompose. Thirdly, as you can see, In the second case, we are getting sodium sulfate, which is an example of the normal salt. And thus, this normal salt, when Na2 sulfate, sodium sulfate is formed, it forms a hard crust layer on the corresponding sulfate, as you can see in the test tube also. So when it will form the hard crust layer, being a poor conductor of heat, will sticks to the glass, and thus we cannot obtain the desired amount of nitric acid. So in short, this method is preferred where the temperature is around or less than 200 degrees Celsius. And the talking in terms of the collection, the concentrated nitric acid vapors condenses. That's why we are using the water tap to maintain the temperature and to condense the vapors and collect it in the water cool receiver. The vapors are condensed here. It would be collected in the from the outlet of the water cool receiver. The identification, how you're going to identify the nitric acid, the vapors of the obtained from the receiver on the heating will gives the reddish brown fumes of NO2. In this test, you won't give the ammonia test, right? You will give the test for NO2 because nitric acid HNO3 will evolve the fumes of NO2, that is the nitrogen dioxide. And the color of the fumes of the nitrogen dioxide is always reddish brown, and it can be tested in presence of acidified iron sulfate, which turns brown, and thus the vapors are identified. Then moving forward, we have the products. When the product we have got is the nitric acid. Pure nitric acid is colorless, while the nitric acid which is obtained in the laboratory is slightly yellowish brown. Generally, these acids are kept in dark colored bottles, so it is not possible to see from the so it is not possible to see from the transparent bottles. So in general terms, they are telling that the pure nitric acid is colorless, and when it is obtained in laboratory, it is slightly yellowish brown. There is a reason that why it is yellowish brown in laboratory and not the colorless, because since preparing this in laboratory, it will decompose because it is a volatile acids. So due to the decomposition of this acid, which is negligible at ordinary temperature but substantial at the higher temperature, right? When we are doing in laboratory, obviously it will decompose because in laboratory we are doing in presence of air under certain conditions, right? So decomposition of nitric acid, how it is decomposed, HNO3 will decompose giving NO2, water, and O2. So this NO2, the test which we do for the nitric acid is for this particular nitrogen dioxide. The reddish brown fumes of nitrogen dioxide are obtained. It results in the formation of the reddish brown fumes which remains dissolved in the acid. These vapors, if we want to condense it, we can. Thus, the yellow brown tint that this particular paragraph is important from the exam point of view. So this particular yellow tint can be removed from the acid which we are preparing in laboratory by the two ways. The first method is by the bubbling of air or the carbon dioxide, and the second method is by the dilution with water. Talking of the first method, the bubbling of the air or carbon dioxide, what is the use of the bubbling? It drives out the reddish brown nitrogen dioxide gas from the temperature and further oxidizes it to the nitric acid. Then we have the dilution with water. This you know very well. Dilution of water means the further we dissolve this particular gas and nitrogen dioxide gas, which is highly soluble in water. So from these two methods, this yellowish tint can be removed. It is very important every time it comes in the paper. Now this is the very important process. Just now we were reading the laboratory preparation, right? And now what we are learning the manufacturing of the nitric acid. They both we are having the difference. I want you to just take 2 minutes and read this laboratory preparation, just 2 minutes.
Yes, ma'am.
Just take 2 minutes and read this laboratory preparation, and then we will do with the manufacturing.
This full Oswald process.
Then we'll continue with the Oswald process. Just take 2 minutes, yeah.
Ma'am, in this process, the concentration of the acid is like a further distillation gives 68% concentrated, right?
Yes.
Okay, how can we, if I want a 99% pure acid, then?
No, we cannot get exactly the 100% acid because it goes beyond the laws. Because everything that is reacting in the air is like there are certain drawbacks of every, like if you're talking machines, we have friction. Similarly, when we are, if we want to obtain the acid concentration up to 98, there is, we cannot obtain every acids up to 98 or 99 or 100%, because some of the heat will be dissipated. There will be certain amount of heat loss, there will be certain amount of decomposition of the acid. That's why there is a certain limit of the acid which we can obtain.
Yes. Yes, I'm done.
Done.
Yes, ma'am.
Okay. Further, this we have learned the laboratory preparation. Now we are continuing with the manufacturing of the nitric acid. Since this is manufacturing, we are going to read. So manufacturing is done in a very large scale. So that's why, as you can see, the entire setup is done in the form of chambers, as you can see, right? The first one, as you can see, is the catalytic chamber. The second chamber is the pipe that goes the oxidation, and the third chamber is our quartz acid chamber. Coming towards our manufacturing, the first step, from the diagram I can show you. So the first step is to introduce, since we are learning the Oswald process for the preparation of the nitric acid. So the gases involved are nitrogen, hydrogen, and oxygen, right? So the first chamber, that is the catalytic chamber, we are going to introduce the ammonia along with the we are going to introduce ammonia along with the oxygen, right? As you can see. Yeah. So this Oswald process, as you can see, we have introduced the ammonia gas along with the oxygen in the platinum catalyst, right? We have nitrogen monoxide and the water.
Yes, ma'am.
Do you want to just have a reading of this and then I'll make you understand? Or you want me first to understand this?
I'll do a quick reading.
First you go through the theory portion. 2 minutes you go through the theory portion and then I'll make you understand this one. Because it is quite long and quite important also.
Do
Right?
they ask the what is the use of this chamber and how many, what are the gases?
Mm-hmm.
Like a quartz chamber, what is the use? Can they ask?
Yeah, not use they can ask.
Like, uh, in properties and usual things which are there in the next part of the chapters, which will be mostly asked in MCQs, right? What is the test for nitric acid?
Yeah, the test they can ask you. What is the respective test of these acids? Test they can definitely ask you. So first you go through the reading, the theory portion. Then
Mm,
I'll make you understand the this one, the diagrammatic portion, because your pre-boards are also going on, so you won't have the time.
yes.
So that's why I'm telling you, just have a reading of this theory portion, because theory, as you can see, it is three-page theory. Just quickly have a reading and then I'll make you understand.
This is bigger than like the sulfuric acid, I think.
Yeah. Or give the react, they can just they can ask you in the opposite way also, that what happens when magnesium react with hot water. So it won't react with hot water, it will react with cold water. So it is nothing that the straight forward questions can be asked. So metals.
You are muted.
Yeah, sorry. So metal when react with the nitric acid gives oxidized product, that is magnesium nitrate and the hydrogen gas. So in this case, nitrogen dioxide cannot be evolved. So normally hydrogen is normally not liberated with dilute HNO3. We have read that hydrogen gets liberated when metals react with acid like HCl and so on. So except for this reaction, because it is generally does not liberate hydrogen. Why? Because nitric acid itself, again and again we are repeating the same thing, it itself undergoes decomposition. It is a volatile acid, so on decomposition forms a nascent oxygen, and thus this nascent oxygen is responsible for the oxidation, and thus it has the oxidation property. Magnesium and manganese, however, react with cold or very dilute nitric acid, these two examples which have been given to us, at the low temperature to liberate the hydrogen gas, since the oxidizing action is seen in these two reactions, and which is done by the nascent oxygen. Dilute HNO3 does not normally give hydrogen on reaction with the metals, but liberate the nitric oxide on reaction with copper. Then we have the chemical properties. The chemical properties all we have studied in metals and acid bases also. When the metal react with nitric acid, gives nitrogen monoxide. Here what happens in with both the table, students they do instead of NO2 they just write nitrogen dioxide, because they just see here it is nitric oxide, evolution of the nitrogen dioxide. Similarly here it is NO2, NO3, here it is NO2. So what thing is to be noticed here is that when the nitric oxide, here we are taking cold nitric acid and here we are taking the hot nitric acid. So when we are taking the cold nitric acid, we are getting nitric oxide, we are liberating, and when we are taking hot nitric acid, we are liberating nitrogen dioxide. Passivity, the pure concentrated nitric acid or fuming nitric acid renders the iron and aluminium passively because of its reactivity. Passivity or inertness is exhibited by some metals. So iron and aluminium are rendered passive, means it is due to the formation of the thin oxide coating over the surface of the metals, which prevents further oxidation. So they just act as a hindered metals. Aquaresia, the same thing, one part HNO3 and three parts of HCl gives nitrosyl chloride and chlorine. This chlorine reacts with the noble metals or the inert metals, gold and platinum.
I
Moving
mean,
forward,
one question it was there like, what is heavy water? So it was this same compound only, like nitro. So what was the name? Like
Heavy water. Heavy
yeah.
water.
Well, they said that give the formula of heavy water, which is found, which is popularly also known as aqua regia in one book paper project.
Heavy water, they asked.
No, they are not. They asked actually, it is formed by one volume of one volume of HNO3 and three volumes of HCl. Just like that. It
So
is
when we
only
are taking, then if we are taking one volume and three volumes, so we will get aquaresia. There will be no hard water, heavy water present here.
I'm sorry, the royal water. That's royal water.
Which water?
Royal.
Royal.
Yes. Give the preparation and how like they asked in the board.
Yeah, it can be named in other ways also aquaresia. It is used for cleansing purpose, so maybe can be called as royal. There's other names also.
I don't know they asked royal water, so that is why I wanted to clarify. It is aqua regia only, right? The answer. Because the
Yeah, it is
compound which
aquaresia
is
only.
formed by one part of HNO3 and three parts of HCl is aqua regia.
Yes, it is
Like
aquaresia.
because water is also formed here and HCl is also there in this
Yeah, when
reaction.
you are, yes, it is correct. When aquaresia we are reading in books, that is a mixture of the two acids. However, the HNO3 and HCl, it can be called as the royal water also, the mixture of the both one. It is
Mm.
correct. In your
So
book, it is not given the royal water, but it the other name is it's
okay.
of aquaregia is royal water also.
So
Then we have
we
the
can write like royal water. When we write aqua
yes,
regia, we
same
can
thing.
say that same
Yes,
thing.
same thing. Then we have the oxidation of the inorganic compounds. Inorganic compounds, like we are having sulfur dioxide, we get the oxidized product sulfuric acid. If we are taking hydrogen sulfide, we have sulfur, water, and nitric oxide. Similarly, we have iron sulfate. Important reaction, very highly important. The ring test which you told me. The iron sulfate with the sulfuric acid and with the nitric acid gives ferrous sulfate, water, and NO. This is the ring test important. This is the ring test which is important. What we have taken is in this reaction we have taken the freshly prepared iron sulfate solution. So this is the iron sulfate solution which is in the liquid form. Iron sulfate solution is on exposure to atmosphere it itself get oxidized to the iron 3 sulfate, and the test will not occur in the case of iron 3 sulfate. For the test to occur we will need it in the form of iron 2 sulfate. So thus the brown ring is formed when we add the sulfuric acid to it in the brown ring. Thus the sulfuric acid being heavier it settles down, right, and thus the iron 2 sulfate layer remains above it, resulting in the formation of this brown layer. So this brown layer is not the sulfuric acid layer. This brown layer is due to the because the acid just settles down, and this brown, the name of the brown ring is FeSO4.NO. Then further this ring is very unstable and it breaks up. And when it breaks up, it again moves down to the acid reaction. And thus this the brown ring of nitroso-ferrous sulfate decomposes on disturbing. Means it is not stable. When you will shake it again, it will dissolve and again it will form. So the reaction is very long, not very long, it is long. It must be learned that firstly we take the ferrous sulfate solution, and when we added the H2SO4, this acid being heavier settles down and it forms a layer of the FeSO4.NO. This is not shown in the reaction, right? It can come in the labeling like in the case study which I told you. So this layer being unstable again breaks up and moves down to acid, dissolve, and we get the FeSO4.3, that is a ferrous sulfate oxidized product with water and nitric oxide. The test which we are going to study for the nitric acid, the first one is it's the red brown fume test, which I told. The decomposition of the nitric acid gives nitrogen dioxide and oxygen. So reddish brown fumes of nitrogen dioxide are obtained. Secondly, if we are going to test for the same, both the things are there, the reddish brown fume, then we have the copper nitrate test. When copper is metal is added to the nitric acid with the heating, gives copper nitrate, H2 and NO2. The last one is the copper nitrate. When in this we add the sulfuric acid, we get sodium bisulfate, so copper nitrate, water, and thus the reddish brown fumes of nitrogen dioxide are formed. Basically, The main test is of the reddish brown fumes of nitrogen dioxide formed. The copper sulfate, this is a secondary test which you can give. So, and also, since the nitric acid is an oxidizing agent, it decomposes due to the formation of the nascent oxygen, the concept which we use for the sulfuric acid. It also brings the formation of the nitric organic compounds by breaking one by reacting it with more hydrogen content. And again, the nitration is done from the xanthoprotic acid, that is also which imparts the yellow color to the skin. Then we have some uses in the form of explosives, nitrates, dyes, drug paints, and synthetic fibers. The name must be learned, that potassium nitrate in gunpowder, ammonium nitrate in fertilizers, and silver nitrate in photography. You might have a clue from the name only. When it is silver, it means photography. General uses, etching designs on the component brassware because it has a solvent, it is an acid. Then pure aqua regia, the another use which you can write. Then in the as a constituent of the rocket fuels. Then we have in the preparation of fertilizer, any 3 or 4 uses can be learned, and that's sufficient. So here our this last chapter, the third part also gets completed. Tomorrow we'll begin with our last part of the chapter.
Yes, ma'am.
Just have a reading. I won't say to go deep. Just have a reading of this thing, of the topic which we learned today.